Cool. Good afternoon. I'm Jay Lee, a master's student from Seoul National University, and I'm excited to present React-Trace, a semantics for understanding React hooks. This is a joint work with my colleague Joongwon Ahn and my advisor, Professor Kwangkeun Yi. So today, React is the go-to framework for building web applications. In a recent Stack Overflow developer survey, about half of the developers said they use React. So please raise your hand if you've ever used React before. Awesome, that's quite a few. But for those who are not familiar, what is React? Let's say you want to build a simple counter. When user clicks the button, the number should be incremented by 1. In traditional imperative UI programming, you need to update an internal state and then manually update the UI after the state gets updated. And as the UI gets more complex, it's easy to create a UI bug where the state and the UI get out of sync. So React frees the developers from this burden by automatically updating the UI when the state gets updated. So in React, we divide and conquer the UI into a view hierarchy to be rendered on the screen. So for us programmers, this allows us to compose smaller views to build a rich UI, and for React, this enables the runtime to efficiently update only part of the UI when the state updates. And a component is a specification of a view that describes how it should look and behave. And component is simply a JavaScript function. So what does it look like? Here's a simple recursive component called bin, short for binary tree, which will be rendered as 2 to n dots on the screen. Like bin, all components should be fully declarative. And as a manual for a view, React runs the component to read it. But a mere act of reading a manual shouldn't trigger a side effect. I mean, if reading the manual for your fridge opened the fridge door, you'll get surprised, right? It's the same for React. React expects the component function to be free of side effects. But any non-trivial UI needs to be able to interact with the user, which is inherently effectful. So React provides a controlled way to declare side effects through React hooks. So we focus here on 2 fundamental hooks, useState and useEffect. useState manages component state. So it takes initial value as input and then returns the current value in the setter function. And useEffect runs the provided closure called an effect after each render. But here's the problem. The semantics of React is quite tricky and subtle. So a component is like a spork, a single function playing two related but distinct roles. So initially, React calls a component to construct a new view. This is used to render the view for the first time. And subsequently, the same component is called, possibly with a different argument, to update an existing view. This dual nature can be confusing because the same function behaves differently based on the component lifecycle. So here's a counter component to illustrate this. So when first called, useState uses the provided argument x to initialize the state s. And when user clicks the button, it triggers a re-render, causing React to call the counter again. But this time, useState performs a completely different task of returning the previous state value. And as a side note, you can simply update a JavaScript variable s to update a state, even if it weren't a const. So all updates should go through the setter function setS. And there are certain rules to follow when using hooks, collectively known as the rules of React. For example, hooks must be called unconditionally at the top level of a component. So this con component here violates this issue by calling useState conditionally inside an if branch. So when you click show, con will re-render and crash the UI. This is because React identifies a hook by its internal position in a linked list, and conditional hook calls violate this assumption. So while React imposes multiple rules and disciplines to make this clever machinery work, providing the abstraction of a quote-unquote declarative functional components, it is still a DSL embedded in a freewheeling language of JavaScript. And this inevitably makes React a leaky abstraction, puzzling many developers. And it's not just me saying this. The most visited question with the React hook tags on Stack Overflow asks about this useState semantics. So now a quick quiz time. This is a code snippet distilled from those questions And note that we're using an ML-like syntax used in our paper. So obviously when the counter is first called, it prints counter followed by, wait a second, my magic wand. It first called counter followed by return. But what will be the order of the printed strings after the button is clicked? Do you think it's update, counter return? Or will it be B, counter return and update? Or will it be C, counter update and return? So if you think it's A, please raise your hand. Okay, there's one. If you think it's B, please raise your hand. Okay, I see 2. If you think it's C, please raise your hand. Okay, I see quite a few. So the answer is C, counter update return. So as you can see, hook semantics can be quite subtle even for us PL researchers. And a common pitfall when using useState and useEffect together is the infinite render loop bug. So there are over 1,600 questions on Stack Overflow asking about useEffect and infinite. So the inf component here demonstrates this issue. So the effect provided to the useEffect hook runs after each render and calls the setter function. So this makes React check whether the state has changed, and if it has, it's gonna invoke inf again. And since the setter function here always updates the state to a new one, this triggers another render followed by the effect call, which creates an infinite loop. So as a result, the UI keeps rendering an ever-increasing stream of numbers. Another common source of confusion is a different kind of infinite render loop bug, caused by directly calling the setter function inside the component body. So the most visited question tagged with React.js and infinite loop on Stack Overflow asks about this very issue. So let's take a look at the inf2 component here. So here the setter function is provided with an identity function, meaning that the state doesn't change. But regardless of that, a setter call inside the component body is hardwired in the runtime to trigger another check by re-executing the component body. So this time, unlike the previous issue, this view never even reaches the screen. So the runtime keeps trying infinitely to read the component body. So to explain and precisely understand these issues, we need to be able to reason about the render semantics of hooks. So we present React-Trace, a semantics that clarifies the behavior of React hooks. So seeing is believing, so here's a React-Trace interpreter and a visualizer we built based on the formal operational semantics. So our visualizer lets users inspect how their program renders step by step, alongside the visualization of the view hierarchy. And you can use the slider to replay the entire execution. And our tool is available online at react-trace.vercel.app. And here's a glimpse of our semantics, which formalizes the React machinery. And don't worry, you don't have to squint. I've made it intentionally small. So we model the React event loop using a small step semantics of transitions of configurations. And we also, invoking the component body is modeled in a big step style, shown on the bottom left. And on the right is the diagram illustrating all the semantic functions and their dependencies, with enclosing boxes depicting the required contexts. So please read our paper for the full details. So, does React-Trace really model React? And the answer is yes. We built a conformance test suite with 38 tests covering 18 scenarios. So these scenarios include edge cases of React. For example, scenario 18, where a child tries to update parent state during evaluation, which correctly results in an error. Moreover, React-Trace does not target a specific version of React. So we validated it against all major versions, including version 16.8 when hooks were first introduced, all the way through 19.1, which was released earlier this March. And all tests passed except for one minor optimization difference in scenario 17, where the order of the prints slightly differed due to the runtime optimization in React. But this is not a defect in our semantics. We could have included this optimization in our React-Trace, but we deliberately chose not to keep the core semantics lean. In fact, we went further and proved in our paper that our semantics matches the optimized one when the components are side effect free. And talking about theorems, we have two conformance theorems about React. So we extracted two key properties of React hooks from the official documentation and show that React-Trace precisely captures both of the properties. So theorem 1 explains the second infinite range loop issue we saw earlier. So a call to a setter function during the evaluation of the component body immediately leads to its re-evaluation. And the second theorem describes the mechanism behind the first infinite range loop issue. If use effects are executed after a re-render triggered by itself or by one of its ancestors updating their state. So React-Trace opens several exciting research directions. First, a semantic-based static analysis and type systems that go beyond current linters. And second, our semantics can serve as a foundation for reasoning about optimizations, including the ones included in the recent experimental React compiler, and also different rendering strategies such as server-side components. And third, we can refine the semantics for pedagogical purposes to help developers build correct mental models of hooks. And last but not least, we can integrate it, use it with existing web semantics for end-to-end verification of web programs. So here are the key takeaways. React-Trace is the first form of semantics for React hooks, validated against real React, providing both a foundation for reasoning about React applications and a basis for future tools. So don't forget to check our online visualizer and bookmark our GitHub repo. And I'm also applying for PhD programs this year, so let's talk if you're interested. Thank you.
Thanks for a great talk. Say questions.
Hi, quick question. Nice talk, and do you see anything in this thing that can be applied to other web frameworks like Vue.js or Angular or Svelte or something, or even like Flutter?
Yeah. This is actually maybe it's an obscure web framework but it's a web framework called Dioxys in Rust, and as you can see, it looks quite similar, right? So we have a discussion in our paper how this can be extended to other frameworks, including something like Dioxys in Rust or like Svelte or other web frameworks. Interestingly, there is something called rules of hooks also in Dioxys. So I think our approach can be applied to other frameworks as well.
Thank you. I'll check out.
Thank you.
Other questions? So you used 35 test cases to verify the semantics?
Yeah, 38 test cases.
38 tests. So is it sufficient to prove the equivalence?
Well, yeah, you can. Yeah, it may seem insufficient, but that's why we have these conformance theorems. So we have theoretical proofs that our model reflects the official React implementation as they describe in their documentation.
Okay.
So you said this works. You gave some examples with some hooks. Does this work for all hooks?
Yeah. Well, our model currently models use state and use effect, and we have a sketch how we can extend this model to other hooks as well. Okay. We designed this to be extensible, so I hope it's going to be straightforward to extend to other hooks, as we've included discussion in our paper.
Okay,
yeah.
Thanks.
Thank you.
Okay, so let's thank the speaker.